Okay. See that one. Not yet.
Usually when it rains like that, it's cooler.
All right. So today we're going to look at chapter 6 in your textbook, thermochemistry. And since there's no lab today, in fact, I handed out the lab for next Tuesday, which will be based upon the topic we're covering today. Then I'll probably have time to finish this lecture today, bleeding over into the lab time. That means that I've scheduled a buffer day coming up on the 29th Thursday. So what I may do is start reviewing on that day so that we're not pressed ahead of the lab on the next Tuesday. All right, thermochemistry. If you're a student of etymology, then you probably have an idea of what thermochemistry means. We're monitoring chemical reactions in terms of the heat that they either produce or absorb. That's the thermo part. So I remember this definition from grade school. What is energy? The capacity to do work or produce heat. And during a chemical reaction, this law holds, the law of conservation of energy. That is, energy can be converted from one form to another, but it can't be created or destroyed. Now that's during chemical reactions, right? We know that energy, now we know that since the 20th century, that energy can be converted into matter and matter into energy, right? But those are nuclear processes. These are chemical processes. So the law of conservation of energy holds for all chemical reactions. The energy, for instance, if a reaction produces heat, it generates heat, that heat's got to come from somewhere. And it comes from the reactants. The reactants have stored energy. And we're going to talk about that in just a minute, how to deal with that. This relates to the first law of thermodynamics. And we're not going to get into thermodynamics per se now. We're going to sort of skim across the surface, learn how to deal with the energy in chemical reactions. And then in the, let's see, I think it's second semester. Yeah. In the second semester, we're going to dig into thermodynamics a little deeper. But this represents the first law of thermodynamics. Another way of saying that is that the total energy, it's often written this way, the total energy of the universe, the change in total energy of the universe is zero. The energy the universe started with is the same amount of energy it has now. The vast majority of chemical reactions involve a transfer of energy. They'll either produce energy, they'll absorb energy. Rarely do you find one that comes out neutral. In other words, with no change in energy. So how do we get a handle on energy transfer? Well, we define potential energy as the, potential means exactly what it says. The energy is there in potential form. In other words, it's not realized. It's stored somehow. One type of potential energy is due to position. Well, abbreviate it like that. Now we're going to introduce concepts of physics here too, just to get a well-rounded understanding of potential energy. Potential energy of due to position is relative height. So my potential energy at the top of a 10-story building is much greater than my potential energy at the street level. And we know that's true because I had to expend energy to get from that street level to the top. So that energy is stored in my position. Now, how do you get it back? You jump off the building. And you'll get all that energy back as soon as you hit the ground. But there are transitions that are involved in the process. And I'm going to get to that in just a second. But anytime you have positional potential energy, you have to have a gravitational field. In other words, if I were 10 stories up on the Earth, I would have a certain amount of potential energy. If I were 10 stories up on the moon, I'd have about a sixth of that energy because the gravitational field is not as strong. And the one we're most interested in is composition. Energy that's stored in various forms, right? When you're relating potential energy to a chemical reaction, it usually has to do with bonds. Right? You have bonds that store energy, and when those bonds are broken or transformed from one type of bond to another, you can get that energy back, or you may have to put energy in. Right? When you make nitroglycerin, you're actually storing energy in those bonds, so that when nitroglycerin goes boom, you get the energy back. So it can go either way. You can also have compositional energy in terms of electrostatic attraction. You can have, let's see, what's a good example? Well, I remember as a kid growing up in Oak Ridge, Tennessee, which was virtually an educational capital of the United States because there were so many PhD engineers and scientists there at the time. This was in the 50s and early 60s. So the educational system there was top notch, right? They weren't going to put up with halfway educating their kids in public schools. So we would take trips, and one of the trips we took was to a science museum. And one of the demonstrations they had was this big Van de Graaff generator. Have you ever seen one of those? The size they used was about this tall. It had a square base and a round tube, and then a big silver globe on top. And what it does is it transfers electric charge to that globe. So once they turn it on, it starts building up the charge. You don't want to get close to it because the voltage difference between you and the globe could be thousands and thousands of volts. So what you do is you put your hand on it and then they turn it on. So you become part of the globe and you're charged as well as the globe. They usually pick a girl with nice long blonde hair. And that's what they did. She put her hand on the globe and they charged it up and her hair started going like that because electric charge likes to bleed from point sources, the tips of her hair. But when it does, they're all negatively charged and they repel one another. So her hair stands up like this. And they cautioned her, don't remove your hand, because if you do, then you start building a charge difference between you and the globe, and the spark will jump. And the shock is not nice. Anyway, we were building electrostatic stored energy in the charge on that round globe. You can store energy in elastics, excuse me, rubber bands like this one. I can store energy in this rubber band. My brother and I used to do it when we were young, right? Shoot each other with, we build, I don't know if you've ever seen them, rubber band guns. just a block of wood, and you put a notch in one end, and then a clothespin is strapped to the other end, and you stretch your thing, and then you play soldier with it. Well, I was older than my brother and more inventive, so he had one that he built. It was a single shot, but I had one that I built. I had 3 clothespins and 3 notches in the front. So while he was loading his, I could shoot him twice. But the stored energy is only released when you turn loose of it, let it go. I'm not going to do it now because I don't want to go chase it. You can store energy in magnetics, in a magnetic field. If you, for instance, if you take 2 magnets, right, we know each magnet has a north and a south pole. And if you bring those magnets together with south to south or north to north, then they're going to repel one another. And it takes energy to push them together. So you store energy in that field as you push them together, and then all you have to do is turn loose of one of them and shoot right off, get your energy back. Then there's nuclear energy based upon the well, actually, it's a complex topic, so I'm not going to go there. But that's stored energy. And there's thermal energy. That's based upon actually the motion of the molecules in a substance. Right? The more thermal energy they have, faster they're moving. In fact, they'll move fast enough to where you can make a solid into a liquid and a liquid into a gas. But that comes in second semester also. So positional energy is one type of potential energy, and compositional energy is another type. Then there's kinetic energy. And I may have mentioned this one before, but now in this context, kinetic energy requires motion. Motion of a mass. And the reason I put it that way is we can calculate the kinetic energy of any moving object. All we need to know is its mass and its velocity. You square its velocity times its mass, and in SI units, right? Mass would be kilograms, right? Velocity would be, it's a derived value, meters per second, and then you square them. Right? Well, we give that a unit. That unit of measure is the joules. We're going to be working in joules when we in either kinetic energy or potential energy. We're going to be talking in terms of joules as a unit of measure for energy. And we can also, this is for, you can visualize this as a single mass, like a bowling ball rolling down the aisle toward the pins. It has a certain amount of kinetic energy when we turn it loose. But you can go to the microscopic scale, and each one of the molecules in a gas or liquid or a solid is moving. Gas is easier to understand because there's lots of distance between them, and they translate from one place to another before they smack into somebody else. So their kinetic energy can be determined, just the mass of the molecule times its velocity squared times a half, and that's its kinetic energy for that individual molecule. Well, there are billions and billions of them, even in a gas. So we don't track individual kinetic energy for each molecule. We can't do it. We don't have the computing power for it. So we base it on statistics, and we simply say a measure of the average kinetic energy for a mass is, let's see, the average kinetic energy. Well, if I were, anybody in here has statistics, I'd probably ask you that beforehand. Okay. When we use a bar over a variable, that means average value of all the kinetic energies. And that is proportional to, there's my proportion sign, is proportional to temperature. So temperature is our measure of kinetic energy of the molecules in a substance. Right, there's our kinetic energy calculation. Now, these are interchangeable. Potential energy and kinetic energy can change places. In our example here, we have a ball that's first in position A, and then there's another ball in position B that's lower. So we know which one has the higher potential energy, right? A does. So if we turn loose of A, it's being held there by some magical force. If we turn loose of A and let it hit B, we would expect the A to acquire kinetic energy equal to its potential energy on its way down. And then it would transfer that kinetic energy to B, and then where would B go? Well, we would expect B to go up to this, can you see it, that level right there? Because that's equal to where A was. If there are no losses in energy at all, if it's 100% transfer, right? But what we observe is that when A hits B, A ends up down on the bottom, and B only goes up to the first level. So what's happened? We can't create energy, can't destroy energy. So we have to account for energy. So the potential energy of A then is equal to the newly acquired potential energy of B plus some difference, right? What was left over here, and it's usually heat. We've converted some of that energy into heat, so all of it can't be delivered to B and move it up to the height that A was. Now, it could happen anywhere. I mean, the heat could go into anything. It could be, you could partially increase the temperature of A and B. You could transfer some of that energy to the surface they're rolling on, but it's there. It's all there. This equal sign is inviolable. Right? They have to be equal in order to satisfy the law of conservation of energy. Okay. Let's see. What am I going to clarify here? Temperature and heat are related. Yes. Oh, okay. Good point. Temperature and heat are related, but they're not the same. Temperature is an intensive property. In other words, when we measure the temperature of a substance, it doesn't matter how much of the substance there is. If it's at 60 degrees Celsius, then if you have this much of it at 60 or this much at 60, it's still 60 degrees. It's an intensive property. Doesn't matter how much you have. Whereas heat, let's see, I haven't given you a symbol for heat yet. Heat is an extensive property. So if we have that substance here at 60 degrees, it'll have a certain amount of heat. But if we have a 60-degree substance at this size, it'll have much, much more heat. All right. Now, how do we know that something has heat in it? The only way we can measure heat is by a transfer of energy. And we do that by measuring the difference in temperature. If we take that 60-degree object and put it outside in 10-degree weather, Celsius, let's make it 0 degrees Celsius, then it'd be freezing. Then some of that heat we know is going to transfer. It always goes from high temperature to low temperature, transferred into the environment. So we've heated up the environment and we've cooled down the object. And how do we know? Because the temperature changed. That's the only way we can measure a transfer of energy is by a temperature change. Okay. All right, so let's get some other definitions out of the way. erase this. Like I said before, I'm going to throw some physics at you because it's unavoidable. The physical definition of work is equal to a force that's acting through a distance. In other words, when you apply a force to something, it has to move. If it doesn't move, then there's no work being done. All right, so let me use their capital F times distance. So force applying through a distance, I think they use a small w here. That's the definition of work. So if I were to say push on this board, right, I'm applying a force, but it's not moving, right? So I'm expending energy and applying it to the board. Since it's not moving, I'm not doing any work. But that energy has to go somewhere. So where's it going? I'm converting it into heat. In fact, the temperature of my hand, the temperature of the board are going up ever so slightly. But that's where it's located, in heat. If you're not doing work, you're making heat. Okay, there's another definition that is a little hard to follow, but I'm going to give it to you anyway. The difference between a state, let's see, these are two functions. Actually, they're functions in the mathematical sense too. There's state function and path function. A state function simply says that all you need to know is the start and the finish. So if you know the energy that you started with and the energy you end up with, you can determine the change in energy, and that delta E is a state function. Doesn't matter how it got there. For instance, if I start in Charleston and before the interstate was completed, the roads might be like this to get up to Beckley. So from the height that Charleston's at, which is, what is it, 500 feet, 600 feet, something like that, up to here, 2,500 feet. I think it's a little higher. Anyway, that difference in height, you've stored energy in your position. And that difference in energy is dependent only on where you started and where you ended. But in order to do work, you've got to apply a force through a greater distance if you go up the curvy road instead of, up the less curvy interstate. That one, this would be a state function. The work function, force times distance, would be a path function. The amount of work required to get there is different for the long way versus the short way. And that's what we mean by state versus path function. This is not the only state function. This is not the only path function. But we're on our way to understanding, hopefully. State function only depends on the difference in the beginning and the end of the state that you're in. And the path requires distance. Now, heat is also a path function. And then the other state function, I have to get to it later because I have to define it for you first. Okay. I'm still on definitions. We got to get some definitions out of the way before we can talk intelligently, and I can say things that make sense to you. So when we talk about heat transfer or even matter transfer, we have to agree upon certain terms. One is the system. We actually usually we define the system. Now, sometimes it comes predefined, but the system is simply everything that we're talking about in this defined region and with these defined conditions, that's the system. Everything else is surroundings. All right, let's see if I got some animations coming. Technically, everything else in the universe is surroundings. There we go. Now I got my animations. All right. However, we find it convenient to isolate the system and the surroundings from the rest of the universe. So that, I mean, we don't even know how big the universe is. So when we say that the surroundings are the rest of the universe, that kind of limits our ability to analyze it. So what we do is we isolate the surroundings and system from the rest of the universe. And what I mean by isolate is nothing gets across that barrier. Matter doesn't cross it, energy doesn't cross it. Then we can talk intelligently about this region versus that region. Okay, now we can look inside and we can define this boundary in terms of what can cross it. Can matter cross it? Right? Or can energy cross it? Under those conditions, if both matter and energy can cross that barrier, then we call that an open system. First one is open. Now, if we say that matter can't cross it, but energy can, right? That one is a closed system. And then we can also set up the barrier so that neither energy nor matter can cross it. And that is the isolated system. All right, we're going to isolate the system next week in the lab. We're going to use 2 styrofoam cups as our calorimeter. I have to define what calorimeter is, but the 2 styrofoam cups will isolate our system in there so that matter doesn't cross, energy doesn't cross. Everything that happens in that Vegas stays in Vegas. All right. So now that we've defined these terms, let's clean this up. Because next I just want to talk about energy. And so energy, if energy, and by the way, let me make this clear first. Whenever, this is important for the sign, when we quantify the amount of energy transferred, then the sign is important. It's all relative to the system. So if something is added to the system, it's a positive number. If it leaves the system, it's a negative number. So if we add energy to the system, that's a positive number. And as far as heat's concerned, it's endothermic. Endo means into. Into heat, goes into the system. And as a consequence, so surrounding loses that heat. Right? The same amount of heat that the surrounding loses, the system gains. The opposite would be exothermic, which means out of. And that would be a negative number. Right? Energy, and we're equating at this point heat and energy, but there is a difference. Okay. So with these 2 versions, this is exothermic versus endothermic. It's important to view all transfers of energy in terms of the system. And that's what this little exercise is hoping to do. Is the freezing of water an endothermic or an exothermic process? If you're freezing water, it's going from what? Liquid to solid. Right? So what do we have to do to make a liquid into a solid? It has to lose energy, right? We have to lose energy. So energy is leaving the system. That means the process relative to the water is exothermic. Well, we define the system as the water. Surroundings are everything else. And which way is the heat flowing? That makes it exothermic. It's an exothermic process. Now, how did we get energy to transfer from liquid water away from it to make the solid? Well, the only way that you can do that is to put it in contact with surroundings that are at a lower temperature, because heat spontaneously goes from high to low temperature. Doesn't go the other direction. So if heat's going to leave the system, this has to be colder than that. That's why you stick your hand in your freezer and it feels cold. Okay, let's look at each one of these. A through E. This concept check has defined the system for me. So in this case, my hand is the system in part A. It gets colder when I touch ice. So is the process endothermic or exothermic? That's my system. Heat's leaving it, right? I feel cold. So it's exothermic. There we go. Ice gets warmer when you touch it. In terms of the ice gets warmer because heat is transferred from my hand into the ice. That's endothermic. Relative to the ice, relative to the system. Water boils in a kettle. If water is the system and it's going to boil, we have to add energy to it. So it's endothermic. Water vapor condenses on a cold pipe. So the water vapor is the system and it's losing heat to the pipe. Heat's exiting the system, has to be exothermic. And ice melts. Ice cream melts. Right? If ice cream's the system, then energy is being transferred into it to make it melt. That's endothermic. All right. And for this one, we need to define the system and its surroundings in order to give a direction. So this first one has methane is burning in a Bunsen burner in a laboratory. So we have a picture. There's our methane burner and there's our tube. And we've got a flame here, right? A double flame. Well, we've also got air being introduced here and methane here. Okay, so what's our system? Well, the gas mixture is our system. So in this flame, as it burns, is heat leaving the system or entering the system? It's leaving the system, right? That's why it feels hot. All right, so that's an exothermic process. How about water drops sitting on your skin after swimming? Then they evaporate. I would argue that the system is the water drops. And heat is being transferred into them from your skin to make them evaporate. So that's an endothermic process. Okay. Let's make some room here. I'll leave that up there as long as I can. Hydrogen gas and oxygen gas react violently to form water. I've mentioned this one before. This is the reaction that sent the space shuttle into low Earth orbit. Let's see. So that's 2 here, 2 here. Well, actually, it had a little help. Right? 2 solid rocket boosters slapped to the side. In fact, those solid rocket boosters are the cause of the Challenge, was it Challenger disaster? They tried to launch the thing in freezing weather. And the O-rings that were holding the segments of the solid rocket together got brittle. So all they had to do was ignite the solid rocket motor and it instantly blew through the gaskets. And then a minute and a half into the flight, the gap had widened enough where it punctured the hydrogen oxygen tank, that big orange thing, and let them mix without control. That's what blew it up. So in this one, is this, first of all, if this is a system, is it going to release energy or absorb energy? It's going to release energy, right? This is an exothermic process. Right? That being said, which is lower energy, the mixture of the gases or the water? Well, here's a way to think about it. I'm gonna give you a value here. This delta H, that's going to represent energy. I'm going to tell you what it means later. But if we put, when you write an equation and it's exothermic, then the heat that's generated is a product. Okay, so with that understanding, you say that heat, where was it? Used to be over here. Right? Now it's over here. That means with a balance of energy, conservation of energy, these two together must have had higher potential energy than that one. Okay. Higher potential energy, lower potential energy with this excess. So the lower energy is in the water. All right. Okay. We mentioned this earlier. Thermodynamics is the study of energy and its interconversions. And it started getting becoming fast and furious middle of the 19th century. And there's your first law again. I don't know why I put that slide in there separate. All right, there's another concept that we can use to try to understand the energy movements in a system or outside a system, transfers. It's called internal energy. The internal energy of this system, which we say is that. The internal energy of that system is supposed to be the sum of all the kinetic and potential energy for that system. Everything. We're accounting for all the energy that it contains. It can also be broken down into two types. It can either be this Q, which is the small letter Q means heat. So this is the symbol for heat. And this one we've defined already. So the work, any work that's been done, any heat that's been generated or absorbed can explain a change in internal energy in that system. Right? We usually don't speak of internal energy as an absolute value like E only, because it's difficult to define relative to what. So we usually speak of it in terms of a change in internal energy. So the change in internal energy can be traced to either heat change in the system or a work done by the system or on the system. Okay. All right, when we quantify these values, either heat or work, there are three parts involved. One is the sign. We've talked about that. The sign tells you which way it's moving, right? This change. Is it moving this way or that way? Then there's the magnitude, which is the number. And then there's the sign. Excuse me. Here's the unit. Those three parts are required for an expression of a thermodynamic quantity. All right. So I'm not going to dwell on this one because I think we've covered it, right? If heat enters the system, it's going to be a positive value. If it leaves the system, it's going to be a negative value. Okay. We can say the same thing about work. If the system does work on its surroundings, then this value is going to be negative. If the surroundings do work on the system, then its value is going to be positive. Now you may wonder, how does the surroundings do work on a system? That's a good question. And the reason, and the way we're going to get a handle on it is to look at it in terms of gases, because gases can expand and contract, and that means motion. So we can measure the movement in terms of compression or expansion. That's where we're going to start our understanding of work on a system, or the system does work on its surroundings. Oops, I got Professor Dave. This was back in his early bearded days. Let's see.
Hey guys, it's Professor Dave. Let's talk about thermochemistry.
He knows a lot about the science stuff. Professor Dave explains.
Thermochemistry is the branch of thermodynamics that deals with the heat absorbed or produced by a chemical reaction. A reaction can either be exothermic, one that releases energy, or endothermic, one that absorbs energy. This change in energy is represented by delta H, or the change in enthalpy for the reaction. For our purposes, we can think of the change in enthalpy as being the change in energy for the reaction, or the energy stored in all the bonds of the products minus the energy stored in all the bonds of the reactants. If there is more energy in the products, delta H will be positive, meaning the additional energy had to be provided, making it an endothermic reaction. If there is less energy in the products, then that additional energy was released, making it an exothermic reaction. Energy, which is the capacity to do work, can have many forms, like mechanical, electrical, chemical, heat, and so forth. And besides quantum mechanical exceptions, energy is conserved. That means it can change forms, like heat energy that evolves when the chemical energy in a broken bond is released. But it won't be created or destroyed. Heat, represented by the letter Q, is a trickier thing to define. But a good way to put it is that heat is the energy that flows between a system and its surroundings due to a difference in temperature. Heat will always flow spontaneously from an area of high temperature to an area of low temperature. For a system, Q will be positive if heat is being absorbed by the system, and it will be negative if heat is being released by the system. When temperature and pressure are constant, Q equals delta H, the change in enthalpy. When we discuss thermochemistry, we will discuss energies in terms of joules or kilojoules. Another common unit used by chemists is the calorie, which is equal to 4.184 joules. 1 calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. This is not to be confused with the food calorie, which is calorie with a capital C. This is actually equal to a kilocalorie, or 1,000 calories, also abbreviated as kcal. A thermochemical equation reports the change in enthalpy for a given reaction in stoichiometric terms. Here, the delta H listed is specific to the molar quantities given by the balanced equation. So if the number of moles of each substance as given were to react, the change in enthalpy would be as listed. To find the enthalpy change for a specific amount of material, just do some stoichiometry. If twice as many moles of material as are listed were to react, then the enthalpy change would also be twice as much as listed. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Next slide. There we go. All right, he used a term there. He actually used the word for the term, delta H, which is enthalpy. We're going to talk about that a little more later and compare it to heat because they're not exactly the same. But we need to get some other stuff under our belts before we can do that. And one of those is to go back to define what work is in terms of the system and the surroundings. How do we get a handle on work that's being done? And here we have a gas that's contained in a cylinder on the right. See, the left-hand cylinder is down here compressed, and that's the initial state. And we're allowing it to expand against a constant pressure. The distance it moved then is against a force. So we can calculate the amount of work that was done when it moved from the smaller unit to the higher unit. Okay. So when it does that, it's actually doing work on its surroundings. When the gas expands, it's pushing against something in the surroundings, which is the pressure, the external pressure, and that's doing work on its surroundings. So the value is going to be negative. Should be negative. There we go. So we have, if work, by definition, is force applied through a distance, then we need a value for force relative to that gas. Right? And what we're saying is pressure is equal force per unit area. That's definition. Well, we need that force. So force is equal to pressure times area. So we can substitute this value in here. Pressure times area is our force. Now, how about the distance that it moved? Well, there's a change in volume, right? And a change in volume is a distance times area, right? Change in volume is how far did it move and what was the area, right? That's the definition of a cylinder, right? The area of the cylinder times the distance it moved, that's its volume. So it moved a certain volume. So if we solve for distance here, then we get a change in volume divided by area. And we can substitute that in here. Delta V with area. Okay. Well, notice this is in the numerator, that's in the denominator. That cancels. So now we have pressure times a change in volume is equal to the work that was done by that gas on its surroundings. Okay. This change in volume would be positive, right? If we say the final volume minus the initial volume will give you a positive number because the final volume is bigger. So with a constant pressure value here, positive, and this value is positive, we're going to get a positive value for work. But we know from our previous definition that work is done on the surroundings, which means work is leaving the system, needs to be negative. So we got to fudge. So that's what we say. We just put a negative sign there, and that makes everything copacetic. Now, what were the units here? Well, pressure, we could say pressure is in atmospheres, right? Even though this force per unit area would be a valid like pounds per square inch, but we're going to use atmospheres here. And a change in volume would be liters. So atmosphere liters would be the unit of measure for this work. But if we want to associate it with other forms of energy change, it needs to be in units of joules. That's why we have this conversion. Liter atmospheres equals 101.3 joules. And remember, whenever you have an equivalence, you have a conversion factor. So let's see, which one of these performs more work? If we have a gas expanding, and I would put, let's see, we need a change in volume would be final minus initial. So the gas is expanding from 1 to 4. So that 4 minus 1 equals 3 liters. That's the change in volume. Pressure then is 2 atmospheres. Right? So our work then would be negative 2 times 3 liter atmospheres, or 6, minus 6 liter atmospheres for that first one. Okay. The second one, we've got, let's see if I have to move that. The second, we've got a change in volume of what? Let's see, it goes from 1 liter to 3 liters. So final minus initial equals 2 liters. And then the pressure it's under is 3 atmospheres. So the work would be negative 3 times 2 equals negative 6 liter atmospheres. So it's exactly the same amount of work. That was the point of that slide. All right. So determine the sign of delta E for each of the following. Okay. Delta E, remember, change in internal energy is equal to heat plus work. For A, we have an endothermic process that performs work. So for A, we have an endothermic process that performs work. Performs. Let's see, is it give? Well, they should say performs work on the surroundings. To be specific. All right. So what would the delta E be if this is endothermic? So there's your Q. And if it's endothermic, the Q would be positive, wouldn't it? Okay. So we've got a positive Q, and performs work on the surroundings is a negative W. Okay. Now, if the value, those are the signs, that's the way they're moving. If the value of work is greater than heat, if this is greater, this is lesser in absolute numerical terms, then what's the delta E? Well, if this is negative and it's greater than that one, delta E would have to be negative, wouldn't it? Yep. If it's the other way around, if this is greater and this is lesser, then the positive wins, and that would be a positive delta E. So in that case, you would see an increase in the internal energy of your system. In this case, you would see a decrease in the internal energy. And then the other way around would be exothermic. I think that's the second choice. B. Work is done on a gas and the process is exothermic. Yes. In this case, we would have a negative Q, and this would be a positive W. Right? Work on system. System work is being done on the system. Then if we say work is greater, the delta E is going to be a positive. And if heat is greater, then the delta E is going to be a negative. Okay? That's sort of a semi-quantitative approach. If I got them right. Negative, positive, positive, negative. Okay. All right. Now we're going to talk about enthalpy. What is enthalpy? Versus heat. Let's erase this one too. Enthalpy and Q are different units. The first difference between enthalpy and heat are that this is a path, excuse me. That's not a path. This is a state function. And this is a path function. In other words, it does depend on how the heat moves from one place to another as to its value. Whereas the delta H just depends on the initial conditions and the final conditions. Now they are related, but they're not the same. Let's see. Well, that's true. The two means of transfer of energy are either Q or W. And W is also a path function. So that's how the internal energy changes. But how about enthalpy? What does enthalpy mean? Think of enthalpy as actually thermodynamic potential. It's going to be in the same units of measure as Q. It'll be in joules. Enthalpy is defined in these terms, mathematically speaking. Right, so enthalpy, change in enthalpy is going to be the internal energy of the system, change in internal energy, plus any change in pressure and volume. So pressure could change, volume can change, or they could both change. And that, I never thought of it before. But does this mean pressure and volume on the system or by the system, or is it internal to the system? I think it's internal to the system. So what we're now going to look at is under what conditions, or are there conditions where the internal energy and the enthalpy are equal? Because this is also a state function. We said that earlier. So if we say delta H is this, and then we take the equivalence of internal energy equals Q plus W. We can put that in here, right there. Okay, so we have that change in the formula. Then if the process takes place at constant pressure, then we can bring this pressure outside the delta sign to where we only have a change in volume. Okay, under conditions of constant pressure, that's what it would look like. Then we've also defined what W equals negative pressure times a change in volume. So if we substitute this one, negative P times delta V, for this value right here, negative P delta V plus P delta V, this is Q. This term cancels this term. And under those conditions, enthalpy and heat are equal. So if your process is being conducted at constant pressure, then you can equate enthalpy and heat transfer. And these are the conditions that chemists prefer to conduct their experiments, because they know that these two are equal if the pressure remains constant. Okay. So even though they're not the same, they are equal under those conditions. All right. Okay. So for this example, let's say you are studying a process that takes your system from P1, V1, T1 to P2, V2, T2. We studied those with gases. So we've got a system that's at this pressure and this volume and this temperature, and it's going to another set of conditions where it has a different pressure, a different volume, and a different temperature. That's the beginning, the premises for this investigation. There are many different paths that you can take between the two thermodynamic states. You can go all over the place. You can change pressure for a while, then change volume, then change temperature, or you could change volume first and then temperature first, or you could change volume and temperature at the same time. So you have lots of combinations that require a different path. So the values of Q and W would differ on the way from here to here, depending on the path that you take. However, no matter how you get from here to here, the delta H will be the same, because it is a state function. So, and that's good for us, because if we want to know what is the delta H for this reaction that we're studying, then all we need to know is what's the delta H for products, right? Final minus initial reactants. Okay, now the kicker here is that change, delta means change. So if you're talking about products, what do you mean change? Right? Relative to what? And we're going to define that. Right? the delta H for the products is dependent upon some standard. Right? What are we considering our standard? And that's coming. All right, this is just a reminder. Delta H equals Q at constant pressure, and delta H equals products minus. Actually, they don't use a delta there, they use an H. Okay, my mistake. But it still has to be referenced to something. So a little bit of stoichiometry here. If we have this equation, this balanced equation, which is the combustion of propane, at C3H8 is propane, and you burn it in oxygen, either in your furnace or in your stove or in your dryer or in your water heater, right? It's going to be the same reaction. It's going to produce carbon dioxide and water, and it's going to give up 2,221 kilojoules. That's a lot of energy for every mole of propane that's burned. And we assume, of course, in air, there's plenty of oxygen, so it's not going to be limiting. Okay, assume that all the heat comes from the combustion of propane. Calculate the delta H in which 5 grams of propane is burned in excess oxygen. So you would set it up, plus your oxygen, yields carbon dioxide and water, and balance the equation. Right? Let's use our budget method. Just so I don't flop around. 3, 8, and 2. This is 1, 2 hydrogens and 3 oxygens. Okay, so if I do carbon, I need 3 carbons here. 3, so that's 6 plus 7 oxygen. And then hydrogens, I need 8 hydrogens. I need 4 here. That gives me 8 hydrogens, and then 4 plus 6 is 10. Is that right? Let's see. 6. Yeah, 10. And then I get 10 over here by 5. So is that right? 3 carbons, 8 hydrogens, 10 oxygens, 6. Yeah, that's right. Okay, so we've got our balanced equation. They already balanced it for me, didn't they? You guys weren't going to say anything. You want to see if I can do it, right? Okay, so the delta H for this is minus 2,221 kilojoules per mole of propane. Now, sometimes you'll see equations written like this, and the delta H will only be the energy units. What they're saying is with the energy units, it's so many kilojoules per 1 mole of propane, so many kilojoules per 5 moles of oxygen, per 3 moles of carbon dioxide, per 4 moles of water. So you can substitute any one of those in here, depending on what you need to do the calculation. Since we need propane, then that's what we've got for our value. And 5 grams of propane, we need to know how many moles that is. Right? Right, so we need a conversion factor with a quotient of grams and moles, and that always means molar mass. Right, so we need 3 times 12.01 for carbon and 8 times 1.01 for hydrogen. I'm not going to trust myself to do that one in my head. 12.01 times 3, 3603, and then 8.08. So this is 44.11. Divided into 5. And I get 0.1134 moles of propane. Now we can multiply that times minus 2,221 kilojoules per mole. Right? Moles cancel. 2, 2. Oops. 2, 1. Is that right? Yep. Let's see, that's a negative. Times. Okay, so I get minus 252 kilojoules of heat that's evolved from 5 grams of propane. Okay. All right. Now, what is calorimetry? Well, Professor Dave defined what a calorie was. So you know it has something to do with heat. And in fact, when I was a student, we did all our thermochemistry calculations in calories rather than joules. So there's been a change from when I was a student to when now it's you're a student. Calorimetry is the science of measuring heat. That's all there is. Metry is the word that means to measure. So we're measuring calories, measuring heat. And in order to do that, we need to know certain things about the objects that are doing the heat transferring, that are at different temperatures. One of those is specific heat capacity. All right. Heat capacity is the amount. Let's start with heat capacity, just heat capacity. This is the amount of heat. Let's see. Transferable. From or to an object. Oops. Per degree C, difference. Okay. This is an extensive property. In other words, you can transfer more heat from a large object for a given temperature than you can from a small object. That doesn't do us much good. What we need is an intensive property. And the way we do it is we take heat capacity and we ratio it to some unit of mass. In this case, we're using grams. So the unit of specific heat capacity is going to be some value, which is joules per gram per degree Celsius. Those would be the units for most. When it just says specific heat capacity, that's what it means. The other possibility is molar heat capacity. And all you have to do to get molar heat capacity is just change that value or that unit. Joules per mole degree C. Now, these are not going to be the same values, but this will be related to the molar mass of the object, if we know it. And this will be related simply to its mass. So if two reactants in a solution at the same temperature are mixed and the resulting solution gets warmer, this means the reaction takes place is exothermic. It gives up heat. An endothermic reaction will get cooler. So we can measure the temperature change during the chemical reaction and determine whether heat was evolved or absorbed. Oh, here comes Professor Dave again. Oops. Sorry. I guess I have to turn him on.
Hey, it's Professor Dave. Let's talk about calorimetry.
He knows a lot about the science stuff. Professor Dave explains.
Different substances absorb heat at different rates due to various structural factors. The heat capacity of a substance is the amount of energy required to raise the temperature of that sample by 1 degree Celsius. A variation of this that is more useful for calculations is the specific heat of a substance, which is the energy required to raise 1 gram of a substance by 1 degree Celsius. Heat, temperature, and heat capacity are all related by the following equations. The amount of heat exchanged in a reaction is equal to the heat capacity of the substance times the change in temperature for that substance. Or, more practically, the heat exchanged is equal to the specific heat of the substance times the grams of the substance present times the change in temperature. We can use this information to learn about heat transfer using a process called calorimetry. For those of you in an introductory chemistry course, you'll probably do some variation of a coffee cup calorimeter experiment. Let's look at how those work. A coffee cup is a pretty good insulator. That's why we use it for coffee, so that the heat doesn't escape so quickly and the coffee stays hot for longer. This makes it possible to take pretty reasonable data about the temperature change in a cup of water when we add a hot piece of metal. We can measure the temperature change in the water and use that information to calculate the specific heat of the metal. So, let's say you heat up a metal by placing it in boiling water at a known temperature until it is just as hot as the water. Then, with tongs, you place it in a coffee cup containing a known volume of room temperature water with a thermometer. The water in the cup will heat up slightly as the heat from the metal flows into the water, and we can record the resulting temperature change. From there, we just do some math. We use the specific heat equation and plug in the data for the water. The temperature change is what you recorded. The mass of water in grams is equal to the number of milliliters of water. And the specific heat of water is a known value. This allows us to calculate the heat absorbed by the water. Well, the heat absorbed by the water was the heat released by the metal. So we can take that same quantity of heat and plug it into a new equation for the metal. That value goes there. We weighed the metal beforehand, and this time the temperature change of the metal is from the boiling water to the final temperature in the coffee cup. So you can solve for the specific heat of the metal. This is useful for identifying unknown metals if you are given a few different specific heats and asked to decipher which metal you are given. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay. That's the way I learned calorimetry. You calculate the amount of heat absorbed by the water, then you equate that to the amount of heat lost by the metal, and use that in a similar calculation. This equation. I got a better way. It's more flexible. But I will say this. We're going to use both of these equations. All right. This is going to be the one with a value that's joules per gram degree C. There. This is going to be in grams. This is going to be in degrees C. All right. So these two cancel that, leave us with joules, so we know the units are right. We're going to use this one for our calorimeter, because the calorimeter while it's a good insulator, it and the thermometer and anything else we put in there that's not part of the experiment will either absorb heat or give up heat. So we've got to find out what that value is so that we can remove that variability and focus on the heat transfer only for the experiment. Okay. And in fact, the first page of the method is what you're going to do first in the lab. I'll tack that onto the front because you have to determine what we call the calorimeter constant before you could proceed. Oh, there's Desiree. What happened to Laura? She was there a second ago. Oh. All right. So this is our construction. We're going to use 2 styrofoam cups. And it's going to have a lid. And it's going to have a hole in the top where you put your thermometer. Now, I used to use this stirring thing, this loop, stirring loop. But some of the reactions we conduct are corrosive, right? And the material I used for my loop was susceptible. So now we don't use the loop. We just stir with the thermometer, right? And if you're careful, you can stir with the thermometer. This is also an isolated system. Remember our definitions. That means that heat and matter, neither one of them can cross the boundary. The styrofoam cups and the lid is our boundary. Nothing gets in, nothing gets out. Everything that happens in there stays in there. That's important for the calculations later. I'll point that out in a second. All right. What that means is that all the heat transferred within that calorimeter must equal 0. Everything that happens in that calorimeter has to sum up to 0 because nothing's getting out and nothing's coming in. All right, so that's where we're at. We have this as a calculation of Q for a substance for which we know the specific heat capacity. And we've measured the mass and we've measured the temperature change. All right. And again, temperature change is always finest minus initial. So the temperature change can be a negative number if the final value is smaller than the initial value. Right. So what we're saying is that everything that happens in that calorimeter is equal to 0. So as many heat terms as you need must add up to, usually there are 3 of them for us, but they can go out to as many as you need. And then this Q is either going to be, usually, this formula or that formula. All right. So let's try to get a handle on this without doing a calculation. If you have a 100-gram sample of water at 90 degrees, 100 grams of water at 90 degrees, and you have a 100-gram sample of water at 10 degrees, and you put them together, where's their temperature going to meet? We got the same mass for each one, and they're the same substance, so they have the same specific heat capacity. So the only difference is the temperature. So where are they going to meet? They're going to meet at 50 degrees, right in the middle. Okay. Now let's make it more difficult. Say you have 100 grams of water at 90 degrees, and you have 500 gram sample of water at 10 degrees. So now this one has, at the lower temperature, there's more of it. So we should expect the temperature to be less than 50 degrees. Because the heat from here is going to transfer here, and it's going to equilibrate at less than 50 degrees because there's 500 grams at the lower temperature. So it's between 10 and 50 degrees. So we can also calculate the final temperature of the water. So let's do that. Let's see. Actually only going to have two terms in here because we're not considering the calorimeter at this point. All right, so 0 equals Q of the hot water plus Q of cold water. Right? So the Q of the hot water is going to be specific heat 4.184, I believe. 4.184 joules per gram degree C times the mass of the hot water, which is 100 grams, times the change in temperature. So the final temperature is going to be what? We don't know yet. Yeah, it's unknown. So let's see. The final temperature is our unknown. The initial temperature is 90 degrees. Okay. Then we have our second Q. It's going to have the same value, 4.184. Only it's going to have a higher mass, and it's going to have a different temperature change. Oops. Minus 10. So that's the thinking part. That's the hard part. The rest is just number crunching. Okay. So we have this one times this one times this one, and this one times this one times that one. So we have two terms come out of that. We're going to have 4.184 times 100. And that's 4.184 times 10 squared T sub F minus, and then I say 90. Minus 3.766 times 10 to the fourth. Plus, now we have 4.184 times 500. And that's 2.092 times 10 to the third times this value. And then that again times 10. And that's a negative 2.092 times 10 to the fourth. So now we want to get the unknown terms on one side and the number terms on the other side. So since these are negative, let's put these two together and move them on this side. Okay. So let me change that sign. Right, this is a negative, that's a negative, so we're going to add them together. And that negative becomes a positive on this side. So that's 5.858 times 10 to the fourth on this side. And then we have this TF and that TF added together. Let's see. 2.023. This is 2.510 times 10 to the third TF. So TF is going to be this one divided by that one. So I get 23.3 degrees C. Let's see if I came close. Oh, I forgot I had it animated. Maybe worked too hard. Yeah, well, they rounded off to two significant figures. Actually, it should be three, I think. Anyway, that's how you calculate the final temperature of the water for this example. And you can string out as many terms as you need here. You have to think, when you put everything into that calorimeter, you have to think in terms of, okay, if it's a hot metal piece, that's separate from the water, that's easy. But if you mix two solutions together, you still have to think of them in terms of, this is a separate solution from that solution in terms of heat and the transfer. Oops. All right, so here's another example. In this case, we have the iron ball. So we would have a different value. If this were the water side and this is the iron ball, that would be a different value for the iron ball. In fact, this would be our no, we're actually given a value here. So we're looking for the final temperature with a different value here, a different mass. This is the same value here with a different mass and different temperatures. And if we do that same calculation, we find out that the water now is going to be 18 degrees instead of 10. So the important thing to realize in all of this, one of the important things is the final temperature in that calorimeter is the same for both, for any of these situations, right? Because they all come to equilibrium by transferring their heat. And the temperature that you measure in that calorimeter is the final temperature for everything. All right. So what do we have next? Let's see how we do it. 2 o'clock. You have a styrofoam cup with 50 grams of water, 10 degrees, and you add 50-gram iron ball to the water. Oh, there's the calculation. I thought it was just giving us an answer, but there it actually shows you the calculation. And then the final temperature will be 18 degrees. I must have stuck that in there because I was tired of doing it. So not only is the final temperature the same for every one of the Q's, you have to be very methodical setting this thing up. That's the hard part. Setting up your equation with everything in its proper place. Then solving the equation is just, just takes a little time. Okay, this is where I would have paused for the next lecture. But we're going to keep going because we have time to do it. So what is Hess's law? Hess's law allows us to predict the enthalpy of a reaction based upon several other reactions that we can add together. I call them component reactions, and produce the final reaction. This is very useful if you suspect that the reaction you want to study is extremely exothermic and even to the point of explosion. So if you can calculate what its value is, that release of heat, then you can actually scale your experiment down to a manageable size rather than put a kilogram of this and a kilogram of that together and stick them in your hood and get them to react and blow the building down. Right. So you could maybe put 10 micrograms together with 10 micrograms of the other, and you can control that better. But you have to know in advance how much energy is going to be released, and that's where Hess comes in. And the reason we can do this is because enthalpy is a state function. We only need to know the end and the beginning. All right. Oh, Professor Dave wants to talk some more. All right, let him explain it and then.
Professor Dave here. I want to tell you about Hess's law.
He knows a lot about the science stuff. Professor Dave explains.
Thermochemical equations can be manipulated to give important data about chemical reactions. We can use them to predict exactly how much energy will be absorbed or released by a reaction, which is very important because we don't want any unexpected explosions. There are two ways we can use tabulated thermochemical data to calculate the delta H of any reaction. The first way requires that we manipulate thermochemical equations in specific ways. So let's be aware of some rules. First, if a reaction has a particular delta H, the reverse of the reaction will have the opposite delta H or the same number with reversed sign. Second, if molar quantities in the equation are multiplied by a coefficient, so is the delta H. So if you double all the substances, double the delta H. These are things we can do to thermochemical data to be able to add equations together to result in a reaction we are curious about. Here's what I mean. Let's say we want to know about the change in enthalpy associated with a reaction, like this one. But it is difficult to measure experimentally. We can take other reactions with known enthalpy changes and rearrange them to align with our equation and get the data we want. The first reaction provided has carbon graphite on the left, which is where we want it. But the equation we want has 2 moles of graphite, so let's double this one. We get 2 moles of everything instead of 1, and we double the delta H. Next, this other one has CO on the right, where we want it, and in the right amount. So all we need to do is add these equations together. The O2 and CO2 will cancel because they are present in the same amounts on both sides, and we are left with the substances in our original equation. Since we added the equations, we also add the delta H's to get the delta H for our equation. This kind of manipulation is allowed by Hess's law. We can manipulate the coefficients of a reaction or reverse its direction in any way necessary as long as we change the delta H associated with it in the appropriate way. Then we add or subtract the equations as necessary to give us precisely the equation in question. The delta H you get by doing the arithmetic will be the delta H for the reaction. Another way to calculate an unknown delta H is to use standard enthalpies of formation. This is denoted by the following symbol, and it represents the enthalpy associated with forming 1 mole of a substance from its respective elements in their standard and most stable state. Most stable state means the most common allotrope, or physical form of an element. So carbon graphite instead of diamond, diatomic oxygen instead of ozone, and so forth. Standard state just refers to standard temperature and pressure, which is room temperature and atmospheric pressure at sea level. That's what is meant by the degree symbol. We can calculate the change in enthalpy for a reaction by adding up the standard heats of formation of the products and then subtracting the sum of the standard heats of formation of the reactants. The heats of formation can be found in your textbook or online, and you just plug them in, multiplying each value by the coefficients in the balanced equation. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
All right, Professor Dave introduced another way of calculating the enthalpy. Standard heat's enthalpies of formation, and I'm going to get to that in a minute. I want to look at Hess's law first. We can carry this. This is what I would call my target reaction into O2. Yep, yields 2NO2 gas. Yep. And the enthalpy of this reaction is equal to 68 kilojoules. But it's a positive value, it's endothermic. Now we have the option of using these two equations. Say we didn't know that value. We could find it out if we use these two equations. And let's look at them. They call this one equation 1, but that's my target equation. So I'm going to say the first equation is the N2 gas plus O2 gas yields 2NO. And the value for this one, the delta H for this one, is 180 kilojoules. The second one is 2NO, and these equations must be balanced. Even the individuals must be balanced first before you can manipulate them. And 2NO2. And this delta H is minus 112 kilojoules. That one's endothermic, this one's exothermic. All right, what we want to do is manipulate the equations in such a way that we can add them together and get that one. Okay, first thing you look for is which is on which side. All right, nitrogen's on the correct side here with oxygen. And for this one, NO2 is on the correct side. And it has some oxygen. So the way they are, if we add them together, will we get what we want? Right, 1 nitrogen, 2 oxygens, and 2 NO2s. So we can do it this way, the long way, plus O2 gas, plus 2NO gas, plus O2 gas. Yields 2NO gas plus 2NO2 gas. And you can see here that you've got the same value there as there. And you got 2 of these here, so you can put a 2 there and cancel that one. So that gives us the same equation there. We didn't have to do anything to the equations to get there. So what we can do is add these together. Right, so that would be 8, 1, 7, 6, 68 kilojoules. Positive. All right. This is just another way to look at it. Because it's a state function, enthalpy is a state function, it doesn't matter how we got there, right? This is a 1-step reaction that we're after, and this is the 2-step that we use to calculate the exactly same value. So this reiterates what Professor Dave was saying. If you reverse the reaction, you have to change the sign on the delta H. If you yeah, the delta H is directly proportional to the quantities of the reactants. So if you have to multiply any one of these by a whole number, then you do the same thing to your delta H. Okay, so in this case, we've got, what do we have? We have ammonia. Okay, Now, remember at the very beginning, we tried to make everything the simplest whole number ratio. Simplest whole number ratio is a good place to start. Sometimes you need to use fractions. And when you use fractions, we're not actually talking about molecules and atoms, because you can't have a fraction of a molecule or an atom. So we're talking about moles. So that's the only way you can interpret a balanced equation if you're using fractional coefficients. We can use those two equations, first two equations, to calculate the enthalpy for the final equation. I think we do that in the next, problem solving. The best way to handle this is work backwards. In other words, when you're working backwards, you're starting with the final equation that you want, and working your way back through the possible component equations to see if they will work and give you the end result that you want. Reverse them if you need to, right? To get the reactants and products on the correct side of the equation, of that arrow. Then multiply if necessary to get the right numbers of moles. So here we go again. We have to multiply this one times 4 in order to give us 2 nitrogens. Notice that 4 times a half is 2. And then we have to multiply this one times 3 to give us 6 waters. And we do the same thing with the enthalpies. So these are the resulting equations here. And if you add them together, let's see what you get. Well, hydrogens cancel. That's good because there's no hydrogen in the final equation. And check our values, like 2 nitrogens there, 2 6 waters, that's good. On the right-hand side, 4 ammonias and 3 oxygens, that's good. And we've already multiplied the delta H's by their factors and add them together, and that will be the enthalpy change for the reaction as written. Now for the standard enthalpies of formation. The standard enthalpies of formation take a standard form. In other words, when you're looking for the standard enthalpy of formation, it's always for a compound or a diatomic. And that's what that 0 means. Delta H 0 of formation. What's the standard enthalpy of formation? What you do is you start with, over here, you start with the compound. All right, so let's use an example, ammonia. How about that? And that is its standard temperature and pressure form. It's a gas, ammonia. And you always start with 1 mole of it. And that stays the same, you don't change that. So then you go, excuse me. Then you go over on the left side and you pull out the elements. What's the nitrogen standard form? Well, it's an N2 gas, right? And hydrogen standard form is H2 gas. Now we can't change these, so the coefficient has to be whatever you need to give you 1 nitrogen. That means 1/2 is your coefficient. And for this one, 3 hydrogens out of H2, right, means 3 halves, right? Because 1/2 of a hydrogen is 1 hydrogen times 3 is 3. So that would be the equation for the standard heat of formation for ammonia, and then you would look up the delta H for that value. It'd be something. Okay, standard pressure is 1 atmosphere. Standard temperature for chemical reactions is 25 degrees. Right? For gases, when we were doing gases, remember it was 0 degrees. It changes for chemical reactions. Now we're at 25 degrees. And if you have any solutions in there, the standard concentration for a solution is 1 molar. All right, so I think this is more confusing than it is helpful. If you're going to react methane, which is this black ball with 4 light blue dots on it, and react it with 2 oxygens, and you break it apart and then you recombine it and you get carbon dioxide and water. But what we've included up here are the standard heats of formation. So I think it'd make more sense if we, there we go. Okay, that one slipped in on me. So in order to determine this value, what we need is the summation of all the standard heats of formation for the products. That's what this sigma means. That's a capital Greek capital sigma. And you want the standard heats of formation for the products. And since the standard heat is in terms of 1 mole of the value, if your equation is pointing to more than 1 mole, you have to multiply it by whatever that value is. So this is for the standard heat of formation for a product. If you have more than 1 product, then you calculate this one and then sum it with the same calculation for the next one. All right, we'll have some examples. Then you subtract reactants. Okay. So in this case, also, you'll notice from that list, if it's an element, the standard heat of formation is 0. Right? Elements are not considered to have required any heat or given up any heat in their formation. That's our 0 point, is the element. So in this case, we've got that expression, and we have sodium hydroxide, and leave the hydrogen off. So we'll have 2 times the sodium hydroxide, which is minus 470. That's the product. And then we'll subtract 2 times the water. And the water is minus 286 kilojoules. And just add those together. And you get minus 368 kilojoules. For that reaction. Right. Let's see. We'll get the bearings here to see how much further. Oh, okay, this is the final discussion. Sources of energy. And there are problems in the review document that we'll look at on, I guess, Thursday. Start looking at them on Thursday. So I'm going to take them in order. So work down. If you only have time to work down through half of them, that's okay. That's probably as many as we'll get to in an hour's time in class. So sources of energy throughout history, sources of energy were kind of limited. Right? We had to use organic materials and burn them. Right? So we would take wood, right, or other types of plant material. We could take dried dung, which is still used in the third world. And in enclosed spaces, it's not healthy. And then we discovered fossil fuels. In other words, organic materials that had been buried in the ground, some form or fashion in the past, and just sitting there waiting for us. They're petroleum products like oil, gas, possibilities. And there's coal. Those are fossil fuels. They're fossilized plant material. And then our technology advanced far enough so that we could harness the potential energy of impounded water, hydroelectric power. When I was growing up in Tennessee, we had numerous opportunities to go witness some of the construction projects that took place when the federal government decided to create this quasi-private or quasi-public unit called the TVA, Tennessee Valley Authority. And they were charged with the responsibility of damming the Tennessee River in strategic locations and producing electricity from it so that rural areas could be electrified. And there are several dams that I visited as a kid. Some of them big and some of them small. But the situation now in this country, at least, is that we've pretty much exhausted our hydroelectric power sources, right? There are no economically feasible projects where you can dam a river and produce hydroelectric from it. That's the first problem. The second problem is that when water is moving at a given speed, it can carry a certain silt load. But when you put a dam in its way, it comes into that lake and slows down, and the silt goes to the bottom. And over time, depending on the silt load that's being carried, it'll fill up. The reservoir will fill up with silt, and it'll have to be dredged out periodically. Otherwise, the dam becomes useless. That was the problem they had in Egypt. When the Russians went in and built them the Aswan High Dam, the Nile River carries a massive load of silt. And when they built that dam, it didn't take 10, 12 years. It was filling up with silt. So they had to go in and dredge it. But there are still some smaller projects that can be built, and many private citizens do that. They build an impoundment, and then they shunt the water downhill a certain grade and run their turbines on it, and they can produce electricity. So it's the difference in here to here. So they don't necessarily impound that much water. They impound it up here, and then they go downhill enough to where they can get a velocity to spin their turbines. And some of them are pretty ingenious to produce electricity on a local scale. And then there's the bad cousin, nuclear. Nuclear power, admittedly in the past, has had its problems. Some of them were created by those who engineered them. And some of them were fabricated, to sell movies. Like meltdown and you have the China syndrome. Well, yeah, the current technology in the US, or the past technology in the US, has been what's called a pressurized water reactor. So you have the coolant is water under high pressure, and you have this huge dome like that. Then you have this little bitty reactor down here, and pressurized water goes in and extracts the heat from the radioactive decay. And then it transfers that heat to another cycle, right? So the pressurized water is enclosed, and it transfers its heat to another cycle that goes to the turbines and generates electricity. The reason you have to have that huge dome is because the water is pressurized. And if you get a leak of any size in that pressurized system, the expansion coefficient for most liquids we take is about 1,000 to 1. Right? It varies. But you need 1,000 times the volume here of the water that's in the system in order to contain. So that's why that big concrete dome is there, to contain any leaks. But the nuclear power, the only thing that's waste in well, actually, the couple of things that are waste in nuclear power, right? The uranium, which is the primary source, produces a radioactive waste that's radioactive for centuries, long time. So you have to get rid of that. But the other waste is heat. Right? That's the only other waste product. If you hear someone complaining about, burning fossil fuels and making carbon dioxide, it's going to kill the earth, right? Which is fantasy anyway. But if you're confronted with someone like that, just ask them where they stand on nuclear power, because it doesn't produce any CO2, right? And if they're against nuclear power too, then you can either walk away, or you can call them a liar, or you can slug them in the face. I don't care, because they're liars. Right? If they really care about the earth, then they would switch to nuclear only. Renewables, which is maybe on the next slide. No, we'll get to renewables in a minute. Renewables are those that have a net zero effluent, like wind power, tides, solar. Right? They can produce electricity without pollutants at their source. The problem is the pollutants that they produce when they're manufactured are massive. Heavy metal pollutants in particular. And then they only have a limited life. So when you have to retire them, you've got all these pollutants that are contained in the technology. What do you do with it? Right? Well, right now we're shipping it to India, where people pick through it, tear it apart, and pull the stuff out, and become sick because of it. And not to mention the fact that renewables are not reliable. They are not expected to be a base load. Okay, so this is the progression of energy sources in the United States. Started off mostly wood. I mean, the whole eastern side of the United States was one huge forest. I mean, you could go from tree to tree to tree and never touch the ground and go all the way to the Mississippi until you get to the grasslands. Then you're in the trees. So we had lots of wood. Now we don't have so much. Coal then started taking over at the beginning of the 20th century. And then it gave way to oil and natural gas, and still is giving way to oil and natural gas. Now, there was a time when the U.S. was energy independent, right? Up until 2020, thanks to Donald Trump. He made us energy independent. And when the Democrats got hold of the White House and half the Congress, then that's when things just turned to crap. Because they're anti-energy for a number of reasons, which I don't have time to discuss here. But they're not benevolent forces. All right. The Earth's atmosphere. What's the Earth's atmosphere made up of? Well, it's primarily nitrogen, 78% nitrogen, 21% oxygen, 1% argon, and then traces of other things. And that's the thing about carbon dioxide as a pollutant, right? There's just a trace amount of carbon dioxide in the atmosphere. It's not enough to have any impact at all on our global temperature. In fact, more effect on our global temperature is provided by water vapor. Clouds will reflect light, and water vapor will hold heat. not just, it's not as efficient as carbon dioxide doing that, but there's more of it, a lot more of it. So they ought to make water a pollutant. So this is what they say is the greenhouse effect, right? Light comes in at a certain wavelength, penetrates the atmosphere, strikes the earth, and is converted to longer wavelengths. And those longer wavelengths are absorbed by molecules in the atmosphere. Now, there is a greenhouse effect in the solar system that's completely run away. That's Venus. But Venus is, atmosphere is composed primarily of carbon dioxide and sulfuric acid. Right? It's hot enough on the surface of Venus to melt lead. But we're nowhere near that. Plus, it's about half the distance to the sun that we are. It's about 48 million miles versus 93 million. So they get a lot more solar radiation too. All right. So what are the possibilities for new energy sources? Well, you can convert coal to gas, right? Right. I've witnessed developing technologies, and it produces a less polluting product out one stream, but there's another stream that's left behind. That's the stuff that you didn't want to get into the gas, right? So what do you do with that? There's always a problem for every fix. Hydrogen as a fuel, that would be great, right? Because when you burn hydrogen, what do you get? Water, that's it. Hydrogen and oxygen makes water. But in order to get hydrogen, where does it come from? Right? We don't have any fossil sources of hydrogen. You have to take water and split it. Into hydrogen and oxygen, right? That's it, 2 and 2. And in order to do that, you need energy. So in order to make hydrogen a useful fuel in our society, we need a cheap source of inexhaustible energy to do this reaction. One of those sources is nuclear. Right? That would work. You can use hydrogen for internal combustion engines. Right? The technology is there. You can use it for fuel cells, which converts hydrogen directly into electric power. Right? There's some technological hurdles for that one, because fuel cells typically have to run at very high temperature, which makes them dangerous. Other alternatives, oil shale, we got lots of that, right? But you have to frack to do it, right? Everybody know what fracking is? You drill a hole into a formation, usually directional drilling. You drill down and then get your drill to go sideways into the formation. And then you poke holes in your pipe, and then you pump drill mud into it of a certain type under very high pressure. And it's so high pressure that it'll crack the rock. And that provides avenues for the oil to come out. Because oil shale is impervious as a for traditional drilling methods. Natural gas, that's also provided through fracking. Right, we can renovate old oil fields that have become non-productive, or we can find new ones and gas fields that are only available if you can frack them. Ethanol, producing ethanol for mixture with gasoline is a no-win solution. The reason being that we make it from primarily corn, and it costs more to make a gallon of ethanol than it does to burn it in your tank. Right? It would not exist without government subsidy. Right? If the government removed the subsidies from ethanol production, the industry would collapse overnight. Right? So what do they say? If you want more of it, subsidize it. If you want less of it, tax it. Methanol is a possibility, right? It's another form of alcohol. Now, Brazil's been making ethanol and burning ethanol in their tanks for decades. They use sugarcane down there. But it only is a viable source because the government subsidizes it. Even there. And it's hard on your engines. It's very hard on the engine parts and on the tubing that transfers the fuel. So you need special types of tubing, and you need special safeguards in your engine to keep it from corroding, because ethanol will absorb water from the atmosphere, whereas gasoline won't. And that moisture is damaging to the engine. All right, seed oil. We can extract oil from seed crops and burn that. In fact, I saw this program where these people got an old school bus with a diesel engine, and they were traveling across the country, and they were doing it every major city. They'd stop and go to a restaurant and ask them if they could have their spent vegetable oil, and they would strain it into the tank, and you'd have to heat it. If you didn't preheat your vegetable oil before you injected it into your diesel engine, it would gum everything up. So they had to preheat it. By the way, when diesel invented the combustion ignition system for a diesel engine, he envisioned it being powered by vegetable oil. It was only later that we refined petroleum to produce diesel fuel. And originally, it was for vegetable oil. Right, so that's one possibility. The photovoltaics, wind, they have numerous problems, right? They're only intermittent sources. Right? Sometimes that windmill out there is just spinning. It looks like it's going to come off its bearings. And other times it just sits there and does nothing. Yeah. Right, so that's intermittent availability. Inefficient storage technologies, right? If it's going to be only available certain times of the day, then you want to be able to store it, right? And that means battery systems. Now, I know Elon Musk is building some huge battery thing in the desert to store with lithium ion batteries. And good luck to him, but I don't think the technology is there to store enough energy.
It's really expensive, but you have to learn to pay it from that, especially if you don't live where there's cell phone service. But when it's off a satellite, my neighbor has it, and I have his Wi-Fi at my house, full blown.
Oh.
So like that took a little bit, but he said he can go for right into my Wi-Fi.
Yeah. Let's see, what's that called? Yeah, he's got thousands of satellites up there. Yeah, to give to world coverage. That's pretty cool. And that's one of the reasons he wants to, not the only, but one of the reasons he's moving ahead with his Starship, because it has much higher capacity. And these satellites have a limited life, so they have to be retired, and that usually means burned up in the atmosphere, and then replaced with newer ones. And the Starship, in fact, they've already working on the technology for dispensing those satellites. It's like this slot in the side of the thing. Look at some of the pictures, and they'll just shoot them out like Pez dispensers.
Where I live, we can't have like Wi-Fi. The carriers didn't offer it. Like Frontier and Suddenlink stuff, and a guy moved close to us and talked to Suddenlink. Well, anyways, they got on internet, but for a long time we had AT&T Wi-Fi, which was just like a mobile hotspot. And it ran well for our plan, but we didn't think we could get that. But places like where some place family where down Mountain View, there's no service at all. As the games,
Yeah.
that'd be great.
Starlink. That's what it's called. The Starlink system. And you need a special receiver to get it. Right? Let's see. Storage technologies. They're not competitive economically. In other words, if the free market were in charge, none of these would happen. It's only through government subsidies that these that's gone blank. Renewables, that these renewables are economically viable. You get tax breaks for like putting solar panels on your house or whatever. Right. And then there are the environmental hazards in production and disposal. Both there's very significant pollution problems. Nuclear is the only one that solves all of these problems. And there are new nuclear technologies that allow you to produce smaller reactors. So you can position the reactors where you need them. In fact, some of them are portable. And you can put them where they'll power like 10,000 homes within a small area, or 1,000 homes. And then you just create another one. They're coming off an assembly line. And you just position them where you need them, right? So you're not on this big grid. You can tie them into the grid if you want. That'd be great. Right? Then you'd have a non-localized energy source would be great for a modern society that had any fear of terrorist attack. Because I mean, how many can they knock out at once? Right? If you have thousands of these reactors around the place, and they're made not with uranium, which can be purified into a bomb or made into a dirty bomb. That's more likely what terrorists would do. They just put some uranium-235 in here and then pack it in with explosives and just spread the radioactive stuff around. And that would kill a bunch of people. But they've got designs where you can use radioactive sources that are not susceptible to that type of terrorist activity. Thorium is one of them. There are 3 times as much thorium in any place on the earth than there is uranium. So it'd be more abundant. And the reactors that are made with thorium cannot melt down. Right. At least that's until we get to the point where we can use fusion. Take like the sun does, fuse hydrogen together and make helium and get lots of energy. We're working on it. Right. I've seen some pretty promising technologies, but they're being developed by engineers that have a sense of economy too. So they're not going to present it. They're not going to develop the technology unless they also, along with it, develop the economics. So when it's mature, when it's ready to go, then it'll be done at a price that we can afford. That's it. That's enough. So we'll come back on Thursday and start reviewing some of these problems and do as much as you can between now and then. I know that's only 2 days time, so you're not going to get through the whole thing unless you've got nothing to do but work chemistry problems. That's not most people. Most students, I should say.